Our class only needs one.
Okay, let's talk about the homework first. So the problem set from chapter 15 and 16 and 17. So we had some conceptual questions. Number 4. A wave moves on a string with a constant velocity. Does this mean that the particles of the string have zero acceleration? And justify your answer. So if we have a string here, darn it, that is anchored at one end, say, and we give it a shake, we're going to send a disturbance that way, and that disturbance has a velocity, and that's what we were looking at with the formula v equals the square root of f over mf divided by L. So the question is, if you pick out some particles here that make up the string itself, this has a constant velocity. So does that mean those particles have no acceleration?
No, because the particles in what are being affected are moving up and down to make the wave happen.
Yep. So while the wave is traveling that way, the particles are actually moving up or down. So they could still accelerate, just not in the direction of the wave that has a constant velocity. So, yes, very true. They would have to accelerate in order to get motion because initially they're still. Number 5, a wire is strung tightly between two immovable posts. Discuss how an increase in temperature affects the speed of a transverse wave on this wire. So here, we have two posts. And we set up, if we pluck it, it would have a wave. Or if we pluck it down here, we could send a wave down. It's sort of like a guitar string. Why would temperature affect this at all? Yes?
Well, wouldn't the heat cause it to expand slightly?
So if something warms up, yeah, it gets larger. If this wire gets longer, what happens to it that might affect the velocity? We'll look down here. What kinds of things happen to it? If it's the same wire, it's just now longer because of the temperature. No.
The higher tension.
Higher tension, why? So if it's longer, would you have to pull it as hard or less hard to get it to stretch? Less hard. So what happens to the tension? Less tension. So as the temperature goes up, we'll say temperature goes up like that, the tension would actually go down. What would happen to this? The M over L is the mass per unit length. We call it a linear density often. What would happen, so if you had a meter of this wire before it was warmed and after it was warmed, which would have a meter of it, either way, which would have more atoms in it? If we took a meter section of each, the cold one would, because they'd be closer together. So actually this would also decrease. So it would depend on the rate that the tension decreases compared to the linear density decreasing as to how the speed would actually change. What if the temperature cooled? You'd get more tension, so tension would go up. What would happen to the linear density? It could potentially go up as well. That one's a little trickier because we might not be able to move. If those are immovable posts, the length would actually be the same. So you could consider a warmer wire might dangle like so, and then each meter of the wire would have a little less mass. But if this is taut, you might not be able to get it any tighter. And so this may or may not change depending on how it was strung in the first place, but it could. And so you'd have the same sort of issue with that. And it would depend on which one's higher or lower, but the temperature could definitely affect it. I would expect the tension to be a bigger effect than the linear density, so that if it got colder, it would get tighter and waves would travel faster because the tension would play a bigger role. If it got warmer and it started to droop, the tension would play a bigger role, so it would go a lot, the waves would go a lot more slowly on it. Number 6, a rope of mass M is hanging down from the ceiling. Nothing is attached to the loose end of the rope. A transverse wave is traveling on the rope. As the wave travels up the rope, does the speed of the wave increase, decrease, or remain the same? So, you have ceiling, rope here, take it and you shake the rope, and you've got a wave going up the rope. What, if anything, will happen?
It would decrease because of gravity.
Okay, so why
it
would
lose its kind of energy that you put onto it?
how come?
Because when you're shaking it, also it's attached to the ceiling, so then it wouldn't be. It would make it harder for it to kind of go back and forth up there.
Definitely, we couldn't do that. But what does that got to do with gravity?
With gravity, because how it's pushing down on it, so then if it goes sideways, then it wants to straighten it out. Gravity does.
But remember when we were looking at projectile motion, if we shot something out that way, although gravity pulled it down, it didn't slow it down in that direction because it's in an opposite direction. So gravity won't slow that part of it down. And while you're right, if we threw a ball here, baseball in commemoration of the Twins' worst start ever, threw that up, it would slow down, but that's the motion going up. It's actually the mass going up, changing our kinetic energy into gravitational potential energy. The mass isn't really moving here. It's just a wave. The mass is staying pretty well horizontal with that because of the strength. So that wouldn't play an effect. Did you have something to add, Morgan?
I was going to say the energy is independent of gravity because energy doesn't really have any mass, so gravity can't pull on it.
Probably fair. Energy does have a mass equivalent, but probably not enough for gravity to affect it in this case. So let's look to other things then. We've got our speed formula again. Same formula as before. This is a uniform rope, so we know that this whole part is staying the same. It's the same number of grams or kilograms per meter of rope. Yeah, no.
As you go up the rope, the tension is higher because there's more rope pulling down on it.
The tension comes from supporting this rope of at mass M. If your wave is here, it's only got a little bit of that rope providing the tension. But if your wave is here, now it's got this amount of rope pulling down on it, so tension should go up. If tension goes up, velocity goes up. So it should actually travel faster the higher it goes because of that, despite the fact that we naturally think of things going more slowly as they rise. Number 9, in a traveling sound wave, are there any particles that are always at rest as a wave passes by? Alex?
Wouldn't it be no because it's a longitudinal? Well, it's not a standing wave.
It isn't a standing wave, you're right. So it's not something that's going to be the same. So if we take a bunch of perfectly equally spaced atoms and apply a sound wave to it, we're going to get a compression moving through that will pull these together, and then behind that an expansion or a rarefaction that will push them apart. So all of these should be moving back and forth as it goes, many times per second, depending on the frequency of the sound. Any questions on those before we go on? Those are some pretty deep thinking ones.
Does sound travel like not as far in water because the particles are more like compact, so like it kind of absorbs?
That is possible. I'm actually not sure on that. I know the speed changes a lot with density, and so the denser the medium, the faster sound travels. I'm not sure if it would dampen it more or less one way or another. But if you've got something solid that you put your head, and don't do this loudly because sound does travel really well. But if you put your head down here, you can very easily hear that thump. That's fairly faint to my ears here, but very loud here. Sound travels really well through solid things. Steel, it travels much, much faster than it does through air. And I think that has to do with that elasticity of the medium. I'm not sure if it travels better through one or not, though.
Does it travel farther?
Or farther, whichever way. So farther just means that it would be audible at a greater distance, so more energy would be preserved. And I'm not sure if that is true or not. I guess I would expect things that are more elastic and maintain their shape better to allow energy to go through more easily, which would mean actually steel would be really good. Water would be better than air because water doesn't really compress. And then air, since it compresses and moves about itself so easily, would be maybe worse. But I'm not sure. Great topic for further investigation.
I know, kind of like to add to that is kind of like when you hear music or something in air, you can kind of figure out, okay, this is where it's coming from. In water, like based on scuba diving and stuff, you hear a noise and you have no idea where it's coming from.
In water, no one can hear you scream.
They can, but they can't understand your words.
But yeah, you can't.
But so I don't know if that is for it traveling better or not. However, what I did notice one of the last times swimming with my daughter is cracking my knuckles. That will go all the way across the pool. That clicking sound. So I bet it does travel better underwater. Sonar works great.
Does the noise matter? Because like whales, like their mating calls.
Very
are like,
possibly the frequency of it does, yeah.
We can go to the Y. Go to the Y.
We should, yeah, go to the pool. I'll have you guys jump in the pool over there.
Male waiting.
Okay, chapter 17. There are some more conceptual questions. Number 2. Suppose you are sitting at the overlap point between the two speakers from a previous figure 17.4. Because of destructive interference, you hear no sound even though both speakers are emitting identical sound waves. One of the two speakers is suddenly shut off. Describe what you would hear. So in 17.4, I think I can picture it, but I'll double check. In 17.4, we've got a receiver hooked up to two speakers that are pointing like so. And they're equal distance from an observation point here. And or not quite equal distance, if they are slightly different and you get different enough to shift one wave so that the maximum or the expansion from one wave is coupled up with the compression from the other, they cancel each other out. This is noise reducing headphones that a lot of people have now. Not when this book was written. If that's the case, then you won't hear anything if they're perfectly attuned to each other. But what happens if you shut that one off?
Behind us.
What happens if you shut one of those off? Do you instantly hear sound? You're shaking your head no. Why?
Well, you won't hear it as soon as because sound travels through air, so it takes a little bit of time.
To hear the silence?
Okay,
Sounds very poetic.
like once the speakers.
We know the speed of sound. What is the speed of silence?
I know the sound of speed.
Yes. He's not wrong necessarily, although he's not perfectly
Didn't say that correctly.
describing his argument. Right. So it would take some amount of time for these sound waves to stop traveling. Thus the sound of silence. And then after they're past, then you would start hearing the one speaker.
That's a good sound.
It is a good sound. I like the original better. Number 14. The natural frequencies of a wind instrument change when it's brought inside from the cold outdoors. Why do frequencies change? And is the change an increase or a decrease? This is a similar question to the wire in the last one. So say you have a flute, or perhaps you are a tromboner. And you have your, that's just a fun word. And you have your trombone out in the car in February and it's very cold. And you come in and you play it, and then as you play it, it warms up. What's going to happen to the sound as you do that? What's going to happen to the sound chamber, and what's going to happen to the sound it produces?
Going to expand and some noises will get flatter.
Well, I don't know what flatter or sharper means, really.
Lower in frequency. Yes, lower in frequency.
Why lower in frequency?
Because you've got more like place for the sound to vibrate around you. Stuff.
So if it's lower in frequency, what else changed about it?
It got bigger.
What did?
The sound chamber.
Okay, so let's take this. Here is my, since I'm a physicist, not a musician, here's my trombone.
Let's see on the trombone this year.
Pretty good, right?
Pretty close.
I'll just put an arrow like this, indicating it could go either way. Um,
Oh gosh.
Well, that's what that was.
mouth goes in there, sound comes out here. I'm not but a simple physicist.
You're also an artist.
And this part slides somehow. And it makes sounds like wah, 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 wah.
Yeah, I'm sure if you asked all the trombones to draw something like that, 90% of them couldn't draw anything better than that.
See, there you go. So, as Morgan said, you bring it in, if it's cold, it's going to shrink up, just like we had talked. The atoms in it move more slowly, they don't push against each other as hard, so the whole thing shrinks. But then as you bring it in, this grows, so the sound chamber enlarges.
It's something you said earlier. Morgan and I had a moment.
He just stared at me and I'm like, oh man, I get it. Stop looking at me like that.
We're going to go move on.
Yeah, please do.
So as you said, the sound chamber enlarges, and the waves here, you guys are weird.
The tornado drill starting.
Pray.
May I have your attention? At 1:45 p.m. today, the National Weather Service has issued a simulated
Oh, God, I
tornado
think it's,
warning
oh, it's
for
happening.
counties. At this time, please proceed.
If this were a real weather event, I would expect all of you to form some sort of human shield around me.
Protect the brain.
I'll be like right next to you like thumbs the whole time. It's great.
Punching bag.
With an instrument like this, we are talking about standing waves. So that's only certain wavelengths that will fit in this. We would have harmonics in this. So in the case of a tube that is essentially closed at one side and open at the other, we could have a quarter wave like this. What else could we have? See if I can draw it like that. That wasn't great.
Water slide.
Something that's open at the other side, so we have sort of one and some quarter number. But if that chamber gets bigger, then the wavelength gets bigger. If wavelength gets bigger, frequency decreases, because velocity is the product of those, and the velocity of the air, of sound in the air, isn't really changing. It does as it's cold or warm, but assuming that we have the same temperature of air in there. So frequency, if frequency goes down, what happens to the sound?
Lower.
It gets lower. I don't know if that means flatter or,
Yes.
okay, flatter. So there you go. Physics.
What was that sound again?
Wah, 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 wah. Okay. The tones, final question here. The tones produced by a typical orchestra are complex sound waves, and most have fundamental frequencies less than 5,000 hertz. However, a high-quality stereo system must be able to reproduce frequencies up to 20,000 hertz accurately. Explain why.
Because if you want to bother every dog in the neighborhood, it helps to blow your whistle into a microphone and just have it radiate over the whole neighborhood.
That is unlikely.
That's the question.
Why, if an orchestra only produces sounds 5,000 hertz or less, why does a nice stereo have to reproduce sounds all the way up to 20,000 hertz?
Amplification.
That's louder. That's not actually a change in frequency.
Because it needs to produce like a blended sound that comes out over 5,000 what
Not quite. The important part here is that most of these instruments, it says, have fundamental frequencies of less than 5,000 hertz. Many of them much less. Overtones. So the other frequencies, so if a string vibrates, you've got a string and its fundamental vibration looks like a half wavelength, so say a violin. It's also at the same time vibrating with that wavelength and with this wavelength, and all of those are making sound and adding to the richness of the sound. So we have to collect some of those too. A human ear can hear from about 20 hertz, which is very, very low, up to about 20,000 hertz. Younger ears typically better than older ears because of the flagella. Another fun word.
Was there like some sort of like sound torture developed way back when where they used really, really low frequency stuff just to like...
Low frequencies I don't think bother us, and as they showed on Mythbusters, there is also apparently no such thing as a brown note.